Around IT in 256 seconds by Tomasz Nurkiewicz. Episode 54. Immutability.
Immutability means that when something was once created, it can't be changed. This concept is tremendously important across our whole industry. Probably you've heard about immutable data structures. Let's take an immutable list as an example. If you create such a list with a few items, you can't add more items to that list. It's written in stone. Any action attempting to modify that list returns a modified copy. The original instance is left intact. Modifying a single item, adding or removing, sorting, each of these operations return a copy. You may think this is terribly inefficient. Naively implemented immutable data structures are very inefficient. Imagine copying 1 million items in a list just to add a new one. However, immutable data structures use one clever technique called structural sharing. In principle, the modified copy of a data structure reuses large parts of the original object. Therefore, more often than not, copying is very superficial. Underneath, a lot of data is shared. Sharing is safe because data is, immutable. Such data structures have some amazing features. If your data never changes, it's absolutely safe to share it between threads. You don't need any synchronization or mutexes. It also means you can easily take a consistent snapshot of your program's state. Imagine you are implementing a computer game. Saving the game to disk is a challenge. Without freezing the entire game, you'll read inconsistent data. But when game's state is immutable, it's trivial. In general, immutability helps tremendously when consistency is needed. By the way, that's why many relational databases take advantage of immutability. For example, PostgreSQL uses multi-version concurrency control. The basic principle of this idea is to keep multiple unmodifiable versions of the same record. Another use case is write-ahead logging, a log of database changes that can only grow but never mutates. Synchronizing this log with multiple machines makes replication much easier. A similar approach was taken by Kafka. Immutability makes its way up the stack. Version control systems like Git take advantage of immutability quite extensively. Effectively, each commit represents an immutable snapshot of the whole directory. Of course, each snapshot shares a lot of data with its predecessors. The same applies to Docker containers. Each container is a set of immutable file system layers. Creating a new container means taking an existing file system and applying another immutable layer. This approach is taken to the extreme with so-called immutable infrastructure. In that case, we never modify production servers manually. Instead, the desired state of production, servers, packages, users, and privileges is defined once. Any change to production environment happens via new definition. The last place where immutability comes to my mind is caching. Cache invalidation is extremely hard, but when you can prove that whatever is cached never changes, there is no need for invalidation. For example, consider cache control immutable header in HTTP response. This is the most effective caching technique. Once stored in your browser or caching proxy, it may live there forever. That's it. Thanks for listening.